In section 4.4, we're going to be solving exponential and logarithmic equations. First, we're going to use like bases to solve exponential equations. Then we're going to use logarithms to solve exponential equations. Then we'll use the definition of a logarithm to solve logarithmic equations. And then we'll get something that's called the one-to-one property of logarithms, and we'll use that to solve logarithmic equations. And then we'll look at a couple of applied problems. All right, first, solving exponential equations by expressing each side as a power of the same base. I call this the matching base method for solving an exponential equation. So if you have a base b being raised to the m power, and that is equals to the same base being raised to the n power, that necessarily means the exponents must be the same thing. So the way we use this method is we first write our equation in the form where the left-hand side of the equation and the right-hand side of the equation are the same base, being raised to powers. Once we have the left-hand side and the right-hand side as the same base, then the exponents are also going to be equal to each other. Once we have set the exponents equal to each other, then we can solve for a variable. Let's look at an example or two. All right, the first example we have here is 5 to the 3x minus 6 is equal to 125. The base on the left-hand side of this equation is 5. The base on the right-hand side of this equation is 125. Those are not the same base. But can I write 125 as 5 to some power? And the answer is yes. 125 is 5 times 5 times 5, which we can write as 5 to the third power. So we can, by writing 125 as 5 to the third power, have the base on the left-hand side of this equation match the base on the right-hand side of the equation. And once the bases on each side match the same number, then I can set the exponents equal to each other. So I have 3x minus 6 is equal to 3. And I solved this equation using the techniques that I have learned this semester for solving this type of equation. So I'm going to add 6 to both sides. Divide both sides by 3. And I get x is equal to 3. Now you can certainly check your solution, and you should. Every equation that you solve, you can check your solution. So I could plug 3 back in for x and determine if this is correct. I have 5 to the 3 times 3 minus 6. That's 5 to the 9 minus 6, 5 to the third, and that is equal to 125. All right, the second equation we have is maybe a little bit more difficult to see what the base could be. On the left-hand side of this equation, I have the base 8. On the right-hand side, I have the base 4. There's no way I can write 8 to some exponent. Excuse me, I can write the 8 as 4 to some exponent. I will spit it out. I can't do that because 4 to a power is not going to give me 8. However, I could write the 8 as 2 to the third. On the right-hand side, I could write the 4 to the second power. So I can match the bases by writing 8 as 2 to the third and 4 as 2 to the second power. So I'm going to do that. And I'm going to put that in parentheses. This is my 8. And I'm raising that to the x plus 2 power. It looks like my screen is frozen. Let me unshare and reshare. All right, there we go. So again, I wrote the 8 as 2 to the third power, and I'm raising that 8 to the x plus 2. So I have 2 to the third to the x plus 2. Now I'm going to write the 4 on the right-hand side as 2 squared. And I'm raising that to the x minus 3 power. Now you have a law of exponents that says that if I raise a power to a power, I multiply the exponents. So if I have a to the n, and I'm raising that to the nth power, that's a to the n times n. So if I raise a power to a power, I can multiply the exponents. All right, so I'm going to do that. So I have 2 to the 3 times x plus 2 equals 2 to the 2 times x minus 3. And now the base on the left-hand side and the base on the right-hand side match. They're both 2. So I'm going to now set the exponents equal to each other. So I have 3 times x plus 2 equals 2 times x minus 3. And I solved this using the techniques that I've learned this semester. I'm going to remove the parentheses, get the x's on the left-hand side and the constants on the right, and then solve. So I'm going to first distribute the 3 across. 3x plus 6. I'm going to distribute the 2 across. 2x minus 6. I'm going to subtract 2x from both sides. I get x plus 6 equals negative 6. I'm going to subtract 6 from both sides. And I get x is negative 12. And I can check this to make sure that this is the correct solution, and I should, by replacing the x in each of my exponents with a negative 12 and see if it checks, and it does check. So my solution is negative 12. And the solution in my first one was. All right, so this is the matching base technique, where I get the base on the left-hand side of my equation to match the base on the right-hand side of my equation. The second method we have for solving exponential equations is to use logarithms. So the first thing you do in this method is you isolate the exponential equation, the exponential expression. That means if you're multiplying your exponential expression by a constant, you need to divide both sides of that equation by that constant. Or if you're adding something to the exponential, you need to subtract that. If you're subtracting something from the exponential, you need to add it to both sides. You need to get that exponential expression all by itself. If you don't, this method is not going to work. Then you look at the base. If the base is 10, take the common log of both sides. If it's any other number besides 10, take the natural log of both sides. Next, step 3 is to simplify using one of the following properties. The natural log of b to the x is x times the natural log of b. Remember, from our properties of logarithms in section 4.3, if we're taking the log of something being raised to a power, we can take that power out of the logarithm as a factor. Also, the natural log of e to the x is just equal to x. Again, what is the logarithm? The logarithm is the power, the exponent, you raise your base to get that value. So what do you raise e to get e to the x? X. Lastly, common log. The log of 10 to the x is equal to x. Just like the previous expression, what do I raise 10 to get 10 to the x? Because the common log is log base 10. Well, the x power is what you'd raise it to. All right, then you solve for the variable. And you should check your solutions. All right, so having sharing problems again. All right, so let's solve this exponential equation. Now, we are not going to be able to match the base because there's nothing I can raise 5 to, no integer or rational number, that will give me 134. So I'm not going to be able to match the bases. So the method using logarithms says if the base that you're raising to the exponent, if your base is 10, take the common log of both sides. If it isn't, take the natural log. All right? So first of all, is my exponential isolated all by itself on the left-hand side of this equation? Yes. There's nothing being multiplied times the 5 to the x. There's nothing being added or subtracted. So it's been isolated. So now I'm going to take the natural log of both sides. All right, so now I have the property, if I'm taking the log of something being raised to a power, I can take that power out as a factor. So the natural log of 5 to the x is x times the natural log of 5. All right, let's pause and talk about what natural log of 5 and natural log of 134 mean. They're numbers. They are real numbers. The natural log of 5 is the exponent you would raise e to get 5. It's a number. Now, it's not going to be a nice, pretty integer or rational number. It's going to be a decimal, an irrational number. So I can only get a decimal approximation to it, but it is just a number. So if I'm multiplying x times the natural log of 5, I can divide both sides by the natural log of 5. It's just a number. So I'm going to do that. All right, so now the natural log of 5 cancels on the left-hand side, and I'm left with x equals the natural log of 134 divided by the natural log of 5. That's just a number. Leaving it written in this form of the natural log of 134 divided by the natural log of 5 is what we call exact. This is the exact answer. Because we haven't found a decimal approximation to either of these logarithms. So that is the exact answer. So if MyMathLab asks for the answer to be inputted exact, that's what you would do. Now, you can take your calculator out and find a decimal approximation to the natural log of 134 divided by the natural log of 5. And when you do that, you get approximately, and I'm going to use the squiggly equals, approximately 3.04. So this is an approximate answer. Because I've rounded it off to a couple of decimal places. All right, so to solve an exponential equation where I'm not able to match base, I look at it and is the exponential isolated? In this case, it was. Then I look at the base. If the base is 10, I'm going to take the common log of both sides. If it isn't, I'm going to take the natural log. Once I take the natural log of both sides, I can bring the exponent out of the logarithm and make it a factor, and then I can solve for the variable. All right, how about this one? 10 to the x equals 8,000. First, is the exponent isolated? Yes. Second, what's the base? The base is 10. So I'm going to take the common log of both sides. All right, what's the log of 10 to the x power? Well, again, the base is 10. So this is, what do you raise 10 to get 10 to the x? Well, this is just equal to x. And that, again, is an exact answer. If I leave it written in terms of the logarithm, that's exact. Now, I could certainly take my calculator out and find a decimal approximation to the log of 8,000, and that's approximately 3.9. So that is my approximate answer. All right. How about this problem? We have 3e to the 7x equals 687. So to solve this, step 1, is my exponential isolated all by itself on the left-hand side? And the answer is no, because I'm multiplying the e to the 7x times 3. So I need to get rid of that 3. And how do I get rid of 3 if it's being multiplied? I divide. So I divide both sides of the equation by the number 3. Now I take my calculator out and I determine what 687 divided by 3 is, and I get 229. All right, now I look at my base, and my base is e, so I'm going to take the natural log of both sides. All right, now the natural log of e to the 7x is just 7x. The natural log base e, log base e of e to the 7x would be just 7x, because what would you raise e to get e to the 7x? Or using the power rule, I can take this out and the natural log of e is 1. All right, now to solve for x, I need to divide the natural log of 229 by 7. And I get x equals the natural log of 229, the whole thing divided by 7. Now, if I'm going to find a decimal approximation to this using my calculator, I need to be sure to close those parentheses, because what you're doing is you're taking the natural log of 229, getting a value, and then you're going to take that value and divide it by 7. So I would take the natural log, and it's going to open parentheses for me, 229, and I'm going to close those parentheses. Make sure that you close those. If you don't close the parentheses, your calculator assumes that you want to divide 229 by 7, then take the log of it. So make sure you close those. Hit your division key, divide by 7, and then enter. All right, so I get approximately 0.78. So again, this right here, x equals the natural log of 229 divided by 7, is exact. And this value right here, 0.78, is approximate. All right, are you ready? Let's solve a complicated one. Now, I like to solve this problem because I continually just want to remind you that the logarithm of a number is just a real number. That's all it is. It's a number. Now, if we leave it in terms of the logarithm, it's exact. If we find a decimal approximation, then it's approximate. So again, the natural log of 7 is just a number. It's just a number. That's its exact value, the natural log of 7. If I took my calculator out and found the natural log of 7, I would find a decimal approximation to it. So this is just a number. Let me erase that, because we're going to need all the space we can get on this slide. All right. First of all, I have exponential expressions on both sides of the equation, and that's okay. But there's no way for me to match the base. I have a base of 3 on the left-hand side and a base of 7 on the right-hand side. Can't match the bases. My bases are not 10, the number 10, so I need to take the natural log of both sides of this equation. Helps if we get our pen working here. Here we go. All right, it's being difficult. All right, so we're going to take the natural log of 3 to the 2x minus 1, and we're going to take the natural log of 7 to the x plus 1. So when I take the natural log of both sides, I get some pretty interesting expressions. Because now, since I've taken the natural log of both sides, and I have something being raised to a power, I can actually take that exponent out as a factor. So when I take this 2x minus 1 out, I need to be sure and put parentheses around it, because that's going to be a factor that I'm multiplying times the natural log of 3. So I'm going to take that out, put it in parentheses. That's being multiplied by the natural log of 3. So natural log of 3 to the 2x minus 1 is equivalent to 2x minus 1 in parentheses times the natural log of 3. And again, the natural log of 3 is just a number. It's just a number. Okay, on the right-hand side, I'm going to take that x plus 1 out. Again, taking it out with parentheses around it, times the natural log of 7. Okay, so now what do we do? Well, any equation that you're solving that involves parentheses, you need to remove the parentheses. And you remove parentheses by using the distributive law. So what you're going to do is you're going to distribute the natural log of 3 across the 2x and across the minus 1. So you're going to distribute this across the 2x and across the minus 1. It's just a number, but we're going to leave it in its exact form. So we're going to leave it written as the natural log of 3. So I have 2 times x times the natural log of 3 minus the natural log of 3. So I removed the parentheses on the left-hand side of the equation. Now I'm going to remove the parentheses on the right-hand side of the equation by distributing the natural log of 7 across the x and across the plus 1. So I get x times the natural log of 7 plus the natural log of 7. Now, if you're solving an equation where your variable is on 2 different sides of the equation, then you need to get your variable on one side of the equation. So I either need to subtract the 2x natural log 3 from both sides, or I need to subtract the x times the natural log of 7 from both sides. And it really doesn't matter which way you do it. I'm going to subtract x times the natural log of 7 from both sides of my equation. And I'm going to do this, unlike I normally write it in columns, I'm going to do this in a row so that it's a little bit easier for us to see. And I'm going to write it right next to the other term that has an x in it. Make it a little bit easier for me to factor here in a second. So I subtracted from both sides of my equation x times the natural log of 7. All right, and so on the right-hand side, that adds to 0, and I'm going to be left with the natural log of 7. On the on the left-hand side, I'm going to do some factoring here. I'm going to factor the x from the first 2 terms. If I factor an x from 2x times the natural log of 3, I get 2 times the natural log of 3. If I factor the x from the negative x times the natural log of 7, I get the natural log of 7. All right, so now I have the x term on the left-hand side of the equation, but I still have this minus natural log of 3 on the left-hand side. So I'm going to add that to both sides. So I'm going to move it to the right-hand side by making it plus. So I'm going to add that to both sides. So I'm just going to write it underneath this time. So I get x times 2 natural log of 3 minus the natural log of 7 equals the natural log of 7 plus the natural log of 3. And I'm almost done, because now I can actually divide both sides of this equation by 2 times the natural log of 3 minus the natural log of 7. Because, again, that's just a number. It's just some number. And you could certainly put that in your calculator and find a decimal approximation to that number. It's just a number. So I can divide both sides by that value. So I'm going to write it up here. I get x equals the natural log of 7 plus the natural log of 3 divided by 2 times the natural log of 3 minus the natural log of 7. And that's the value. That's the exact value for x. You can find a decimal approximation to this also, but that is its exact value. Now, you could, it's good practice, although MyMathLab doesn't require it, you could look at this and say, but can I condense this? And the answer is yes, you could condense this. You could write this as the natural log of 7 plus the natural log of 3. You can write the sum of 2 logarithms as the logarithm of the product. So you could write the numerator as the natural log of 7 times 3, which is the natural log of 21. All right, down in the bottom, you have 2 times the natural log of 3. You can take that 2 inside the logarithm as an exponent, so you can take that in. So that would be the natural log of 9 minus the natural log of 7. And you can take the difference of 2 logarithms and write that as the logarithm of a quotient. So you could write the denominator as the natural log of 9/7. I might put that in parentheses so that I know that I'm taking the log of 9/7. You could do that. Certainly MyMathLab would not require you to do that, but it's good practice to show you that yes, you can condense logarithms. You can take the sum of 2 logs and write that as the log of a product. You can take a factor of a logarithm back into the logarithm as a power. And then you can take the difference of 2 logarithms and write that as the logarithm of a quotient. And we're done. We can't do anything else to that. All right, was that fun? Wasn't that fun? Yes, it was. Again, why do I do this problem? I do this problem to show you that even though it looks complicated, and perhaps you think it is, but these are all just numbers. If instead of over on the left-hand side of this slide, instead of having 2x times the natural log of 3, if that were just the number 3 instead of the natural log of 3, you wouldn't have any problems with it. You say, oh, that's 6x. It's just a number. It's just a number. So just like 6 is a number, the natural log of 3 is just a number. So I can deal with numbers no matter what form they're in, whether they're just a nice pretty integer or if they're in terms of a logarithm. I can deal with those. All right, so using the definition of logarithms to solve logarithmic equations. Now, I'm going to warn you about 9 million times about solving logarithmic equations. When you solve a logarithmic equation, you must check your solutions. Unlike exponentials, whose domain is the set of all real numbers, remember from section 4.1, we deliberately restricted the base to be positive and not equal to 1, so that the domain of the exponential is the set of all real numbers. No restriction on the domain. However, the range of the exponential was from 0 to infinity, not including 0, the set of positive numbers. When we found the logarithm is the inverse of the exponential. So the logarithm's domain is the set of positive numbers. You cannot take the logarithm of 0. You cannot take the logarithm of a negative number. So when you solve a logarithmic equation, you must check to make sure that the value you get for your variable is not a restriction on your domain. All right, you have to check your solutions. All right, so how do we solve a logarithmic equation? First, express the equation in the form the log isolated by itself on the left-hand side is equal to a constant. So log base b of m is equal to c. Second, use the definition of a logarithm to rewrite the equation in exponential form. Remember, what is the logarithm equal to? The logarithm is the exponent that you raise that base to get the value you're taking the log of. So log base b of m equal to c. C is the exponent you raise the base b to get m. So b to the c equals m is the exponential equivalent to that logarithm. Once you have it in exponential form, solve for the variable and then check your solutions. You have to check your solutions to make sure that you're only taking the log of positive numbers, that it's not violating the domain of the logarithm. All right, so let's solve this simple logarithmic equation. I have log base 2 of x minus 4 equals 3. So let's write this as an exponential. My base is 2. That is my base. I am raising that to the third power. This is my exponent. So 2 to the third, and that's equal to what I'm taking the log of, x minus 4. Simple linear equation to solve. 2 to the third is 8. Add 4 to both sides, and I get x is 12. All right, I'm going to do a quick check. I'm going to go up here and erase what I've written over here so we can see the original equation. I'm going to do a real quick check to make sure that putting 12 back into that logarithm doesn't violate my domain, and it doesn't. If I substitute 12 back into the original equation, I'm fine. I'm going to get log base 2 of 12 minus 4 is equal to 3, and that is going to be the log base 2 of 8 equals 3, and that's true. That is correct. Because what is the logarithm equal to? The logarithm is equal to the base I raised that, excuse me, the exponent I raised that base to get that value. So 2 to the third equals 8. That is true. All right, but I have to check my solution. Once I get an x, I need to do a quick substitution back into my equation to make sure that I'm not trying to take the logarithm of a negative number. All right, let's see if we can't solve this one. All right, so first thing you need to do is have it in the form where you have the logarithm isolated on one side of the equation equal to a constant. That's not the case here. I have that factor of 4 outside the logarithm on the left-hand side of the equation. So I'm just going to get rid of that by dividing. So I'm going to divide both sides by 4. The 4 cancels on the left-hand side, and I'm left with the natural log of 3x. 8 divided by 4 is 2. Now I'm going to write this in exponential form. So my base, the base of the natural logarithm is the number e. The power that I'm raising the e to is the second power, and that's going to be equal to what I'm taking the log of, which is 3x. Now I need to solve for x. I would do that by dividing both sides by 3. And I get x is equal to e squared over 3. And that is an exact answer. If I wanted to find a decimal approximation to that, I would go to my calculator, I'd square e, and then I divide that result by 3. And this is not going to cause an issue with my domain. E squared divided by 3 will be a positive number. So when I replace x with that positive number and multiply it by 3, that's still going to be positive. So it's going to be the logarithm of a positive number, and that will be okay. So this is the solution. So again, what am I checking? I'm just checking to make sure that my x cannot be something that's going to make this negative. Because the domain of a logarithmic function is the set of positive numbers. So I can't have a solution that's going to have me taking the logarithm of a negative number. All right, so let's see if we can't do this problem. And you do have a problem similar to this on your exam. So this is a really good one for you to practice in homework and on a quiz. And of course, doing the exam review. So I have the log of x plus the log of x minus 3 equals 1. Now, to be able to write this as an exponential, I must have a single logarithm on the left-hand side of the equation, and I do not. I have the sum of two logs. But I can condense this by using the product rule of logarithms. If I have the sum of two logarithms, I can condense that to a single logarithm by writing it as the log of a product. So I'm going to do that. I'm going to take this sum of two logs, and I'm going to write that as a product. So I'm going to have the log of x times x minus 3, and that's going to equal 1. All right, now I'm going to go ahead and multiply this out if I want to. This is the log of x squared minus 3x, and that is equal to 1. So now I'm going to write this as an exponential. So my base is the number 10. This is the common logarithm. And I'm raising that 10 to the first power. This is my exponent. And that is equivalent to what I'm taking the log of, which is x squared minus 3x. This is a quadratic equation. And it's a quadratic equation because it has an x squared in it. So how do you solve a quadratic equation? You're going to put this in standard form. You're going to get everything on the left-hand side or the right-hand side and 0 on the other. Then you're going to either factor it or use the quadratic formula. And this is factorable, so I'm going to factor it. So I'm going to write it up here. We have 10 equals x squared minus 3x. 10 to the first power is 10. I'm going to subtract 10 from both sides. Just rewrite it. X squared minus 3x minus 10 is equal to 0. That factors to x minus 5, x plus 2, I believe. Does that look correct to you? FOIL it real quick to make sure it looks good. Set the x minus 5 equal to 0. The x plus 2 equal to 0. Add 5 to both sides. You get x is 5. Subtract 2 from both sides. You get x is negative 2. All right, so now I do a quick check. Because I have to make sure that I'm not violating the domain of the logarithm. So I got x is 5 and x is equal to negative 2. So I have x is 5 and x equals negative 2. Do either one of those violate the domain? Well, negative 2 would. Because I can't take the logarithm of negative 2. So if I substitute the negative 2 back in to the original equation, that is not true. This violates the domain. Because the domain is from 0 to infinity, set of positive numbers. However, 5 is fine. 5 works. Log of 5. 5's going to blow up. The log of 5 plus the log of 5 minus 3. Is that equal to 1? What's the log of 5 plus the log of 2? And that is equal to 1. You can take your calculator out and do a decimal approximation, and you should get 1. Or, since you know the sum of two logs is equal to the log of the product, this is the log of 10. 5 times 2 is 10. And the log of 10 is 1. All right, the one-to-one property. Oh, I got a text message coming through. Sorry about that. Number 1, express the equation in the form of log equals log. This form involves a single logarithm whose coefficient is 1 on each side of the equation. I think I'll put myself in airplane mode here real quick so no more text comes through. There we go. Express the equation in the form log m equals log n. That means that if you have multiple logarithms on one side of the equation or the other, you're going to condense those using your properties of logarithms. If you have the sum, you're going to condense it to a product. If you have a difference, you're going to condense it to a quotient. All right, this form involves a single logarithm whose coefficient is 1 on each side of the equation. Use the one-to-one property. What is the one-to-one property? The one-to-one property says that if you have the log base b of m equal to the log base b of n, then necessarily m has to equal n. Solve for your variable, and then be sure you check your solutions. Whenever you solve, I told you I was going to say it a million times, whenever you solve a logarithmic equation, you must check your solutions to determine whether or not you're violating the domain of the logarithm. Okay, so we're going to solve the natural log of x minus 3 equals the natural log of 7x minus 23 minus the natural log of x plus 1. Now, you can handle this a couple of different ways. You could add the natural log of x plus 1 to both sides of the equation so that you have the sum of two logarithms that you can write as a product. That might be beneficial. Or on the right-hand side, you can just condense those two logarithms into the logarithm of a quotient because you have the difference of two logs. So you can handle it either way. I could add the natural log of x plus 1 to both sides and get the natural log of x minus 3 plus the natural log of x plus 1 equals the natural log of 7x minus 23. And I can combine these. I can condense the left-hand side by writing that as a product. So that's the natural log of x minus 3. Good thing I have an eraser, huh? Equals the natural log of 7x minus 23. So now that I have it in the form where I have log equals log, then what I'm taking the logarithm of has to equal. So in this case, x minus 3 and I'm going to solve that. That's going to be quadratic because you're going to FOIL the left-hand side of this, and then you're going to get the 7x over on the left-hand side and then minus 23 on the left-hand side, and you're going to solve it that way. So we could do that. I'm going to FOIL the left-hand side. That's going to be x squared minus 2x minus 3. I'm doing my outside and inside in my head. And that's equal to 7x minus 23. Subtract the 7x from both sides, add the 23 to both sides. And I get x squared minus 9x plus 20 is equal to 0. And that's factorable. It's going to be x minus, what's that, 4 and 5. So I get x is 4 or x is 5. And both of those are okay. Neither one of those are going to cause me issues with my domain. If I replace x with 4, then I'm fine. If I replace x with 5, then I'm fine. I'm not going to be taking the logarithm of a negative number. Okay? So both of these are okay. If I let x equal 5, the natural log of 5 minus 3 is fine. The natural log of, what's that going to be? 35 minus 23, that's fine. Minus the natural log of 5 plus 6, that's 5 plus 1, 6, that's fine. None of these are going to be the logarithm of a negative number. If I put 4 in there, that's fine. What's that going to be? 28 minus 23, that's fine. Not a negative. Minus the natural log of what? 4 plus 1, that's fine. And all of these actually check. the 4 and the 5 are both solutions. Now, the other way you could have handled this, and I do want to show you that also, is to write the right-hand side as a quotient. And the only thing that's different is you're going to have to multiply both sides by the least common denominator. So let me do a little bit of erasing here. All right, so now instead of moving the natural log of x plus 1 to the left-hand side, I'm just going to write the right-hand side as the logarithm of a quotient. It's probably a little bit quicker to do. The difference of two logarithms can be written as the logarithm of the quotient. So now that I have log equals log, I can set what I'm taking the log of equal to each other. And this is a rational equation because I have a rational expression on the right-hand side, but I can multiply both sides by x plus 1, and I get the same thing that I did before. The x plus 1 cancels on the right-hand side, and I get exactly the same equation that I had before. Exactly the same equation. Just a different way of approaching it. All right, a couple of applications. How long to the nearest tenth of a year will it take $1,000 to grow to $3,600 at 8% annual interest compounded quarterly? So we got the compound interest formula for discrete compounding periods in the first section of this chapter. And that formula looks like this. The amount accrued in an investment is equal to the principal times 1 plus the interest rate expressed as a decimal divided by the number of compounding periods that you have, raised to the number of compounding periods you have times the number of years that you're investing this money, how long you're investing it. And in that early section, section 4.1, we had all the information that we needed except A. We knew what principal we were investing, we knew the rate, we knew the number of compounding periods, we knew the time in years that we were investing. Now, we don't know what the time is, so we're going to be solving for t. So this is going to be an exponential equation because the variable I'm solving for is in the exponent of my equation. So I'm going to replace all the values I know and solve for t. So what are we doing here? How long will it take $1,000? So our principal is going to be 1,000 to grow to 3,600. So that's how much we're going to have in our account after so many years. So that is A. Our interest rate is 8%, but we have to write that as a decimal. So that's 0.08. Remember, to write a percent as a decimal, you divide by 100. And we're compounding quarterly. That means 4 times a year. So N is 4. So now let's make all those substitutions. 3,600 equals 1,000 times 1 plus 0.08 divided by 4 to the 4t. So we're solving this equation for t. So I need to do a few things before I can actually take the log of both sides, which is how I'm going to solve this. I'm going to go ahead and get a decimal approximation. Well, actually, it's going to be an exact decimal of 1 plus 0.08 divided by 4. So I'm going to go ahead and take my calculator out and do that, and I get 1.02. All right, to solve an exponential equation, I need to have the exponential isolated by itself on one side of the equation. So I need to get rid of the 1,000. So I'm going to divide both sides by 1,000. 3,600 divided by 1,000 is 3.6. All right, so now that I have the exponential isolated on the right-hand side of this equation, I can take the natural logarithm of both sides. All right, when I take the natural log of something being raised to a power, I can bring that power out as a factor. So I can take this 4t and bring it outside the logarithm. And now if I'm solving for t, I can divide everything. I can divide both sides by everything but t. So on the right-hand side, I have 4 times t times the natural log of 1.02. So I can divide by 4 times the natural log of 1.02 and isolate the t. Okay, so I get t is equal to the natural log of 3.6 over 4 times the natural log of 1.02. And I need a decimal approximation to that. This is a real world problem. So you're not going to want to leave it as an exact value. You're going to want to find a decimal equivalent to that. So when I do that, I take my calculator out and I take the natural log of 3.6 and I divide that by 4 times the natural log of 1.02. I get approximately 16.2 years. So if I invest $1,000 at 8% compounded quarterly, it's going to take 16 years for that to increase to $3,600. All right, the second application problem is one that we looked at in a previous section, section 4.2, but this time we're going to look at girls, and we're not solving for f of x, we're going to actually solve for x. The percentage of adult height attained by a girl who is x years old can be modeled by f of x equals 62 plus 35 times the log of x minus 4, where x represents the girl's age from 5 to 15, and f of x represents the percentage of her adult height. At what age, so you're going to be solving for x, it's asking for what age, which is x, has a girl attained 97% of her adult height. So they give you the percentage, which is f of x, and you're going to solve for x. So we're going to set our equation up. And they give me 97. That's f of x. And we're going to solve for x. So to solve a logarithmic equation, I want to isolate the logarithm and then write it as an exponential. So I need to get the 62 out of there, and I need to get 35 out of there. So the first thing I'm going to do is subtract the 62 from both sides. And this works out really nice. To divide both sides by 35. Wasn't that convenient that we made that equal to 1? So on the left-hand side, we get 1 equals the log of x minus 4. And now we're going to write this as an exponential. The base of the common log is 10. So our base, 10, we're going to raise that. That is the exponent right there. 1, raise that to the first power, and that's going to be equal to what we're taking the log of. So we have 10 equals x minus 4. Add 4 to both sides. And x will be 14. And I don't know about you guys, but that actually is true of me. When I was 14 years old, yes, I was just about the same height as I am now, which you've seen me in person. I'm pretty tall, but that is true. At 14, I was pretty much the height that I am today. All right, and that ends section 4.4 on solving exponential and logarithmic equations.